All right, hi everyone. This will be my last video for this week about interpreting radial wave functions. I will tell you that everything that I'm going to talk about here is described in the worksheet problems for today's class. So my advice to you would be to go through and do those. You can follow along here, but you should do the problems. I think it will benefit you. So the first problem asks you to explain the units of the hydrogen atom wave function. What kind of quantity is it? Exponential terms are unitless. You can look at this. It has a Bohr radius in it, A naught. And what you might convince yourself of pretty quickly is that psi has units of 1/meter cubed to the 1/2. Okay. Well, where does this come from? Remember, psi squared is a probability density, which is defined with respect to a generalized volume element, d tau. Hydrogen atom is a 3D problem. So in 3D space, d tau is a volume element. So the square of the wave function is a probability per unit volume. That is, it's a probability of finding the electron in some really small space, some sphere. Now, if you've done some linear algebra or maybe some advanced physics, you might know this Cartesian to polar conversion. But in 3D polar space, d tau, the volume element, has this formula. D tau is equal to r squared sine theta dr d theta d phi. And if you don't know that or don't have it memorized, put that in your notes and circle it. It'll end up being important. All right, consider the probability of finding an electron in a sphere of volume 1 cubic picometer located at the nucleus of a 1s, 2s, and 2pz orbital. Without doing any calculations, rank these in order of increasing probability. Well, here's how it goes. 2p less than 2s less than 1s. Right? And why is that? Well, the 2p, remember, is 0 at the nucleus. 0, I guess. 1s and 2s are both non-zero. 2s is more spread out. Right? So because it's spread out, it's lower at the origin, and 1s is the highest. Assuming these wave functions are constant, calculate the probabilities. Here are those numbers. And again, I'm not going to work through that here. It's a pretty simple calculation. When we say assume it's constant, that allows you to make some simplifications. So there should be no calculus involved in this. But if you do it right, you get these numbers and you'll see that they match our expectations exactly. 1s is highest, 2s, 2pz. If I considered the same sphere at radius r equals a naught, explain how these probabilities would change. Well, if I go out to a naught, what you'll find is that the 2p is now increasing. So 2p is 0 at the origin and then it increases. Whereas the 1s and 2s will both decrease. As I increase along the radius, those ones are both decreasing. My own guess is that the 1s will still be the biggest, right? And whether or not 2s or 2p is bigger is a little hard to tell, but that's sort of what will go on. Again, go through and do this. You should calculate these values, but here you go. You'll find that 1s is 2.9 times 10 to the minus 7. 2s and 2z, in fact, are equal, 2.5 times 10 to the minus 8. Here's the next question. Given the previous calculations, is it correct to say that it is more probable to find a hydrogen 1s electron at the nucleus than at a radius of a naught? Explain. And on the surface of it, this is a dumb question. 10 to the minus 6 is bigger than 10 to the minus 7. So you would say this has to be bigger. We need to think about this carefully. These are these old merry-go-round things when you were a kid. And if you were anything like me, you rode on the edge of this because that's where it was funnest. That's where it went the fastest. Why does it spin faster at the edge, even though it's moving at a constant frequency? It's spinning at the same rate, but you do go faster at the edge. Well, the answer is simply that there's a larger circumference. So the speed is the frequency times the circumference. Probabilities work the same way. Remember that the probability is equal to the square of the wave function times the volume element. And when I talk about a radius at r equals a naught, that volume element is not the same as at r equals 0. Right? Let me show you what I mean. Here's a 1s orbital. Okay. At the origin, there's just a little sphere. Right? But if I go out to r equals a naught, there are a whole bunch of possible spaces. And this is not only in this plane, but it rotates in 3 dimensions. Right? If I went to some other R2, that space would get even bigger. Right? I've kind of moved out further on the merry-go-round. And so the answer to this question is here, right? The answer is no. The radial wave function, or really the square of it, it's a probability density, probability per unit volume. It expresses the probability of finding the electron in some small sphere, right? A point. It is true that the probability per sphere is smaller at a naught. The wave function is decreasing. This is what we calculated here. But there are a lot more of those spheres on the surface at r equals a naught compared to r equals 0. I tried to represent that here. Right? At r equals a naught, I can get a bunch of these infinitesimal volume elements right on that surface. It turns out that this geometric factor wins out and causes the most probable radius to occur at something other than 0. So the wave function's decreasing exponentially with r. The surface area is increasing with r. It goes as r squared. And the winner is a trade-off between those two effects. How do you handle this mathematically? Well, start with your postulate. P equals psi star psi d tau. I then plug in what I mean by this. It's 3D space, so it's a triple integral. Right? My wave function is r times y. So I get psi star psi, and then my volume element is r squared sine theta dr d theta d phi. You then group your terms. All of my radial dependence here and all of my angular dependence here. This is describing the angular dependence. This, all that stuff inside here, is describing the radial dependence. And so this leads us to define a new function. Right? It's called the radial distribution function. In an unfortunate selection of variables, it's called rho. So rho is equal to n, some normalization constant to adjust its height, little r squared times big R squared. You can analyze the units here and you'll find out that this has units of 1/meter. Right? So it is a probability per unit length. And it describes the probability density of finding an electron at some radius. So when we want to think about, what radii do I find an electron at, I need to think about radial distribution functions. These are also plotted on your sheet. Right? And so here they are. Right? 1s has simply one hump and looks like this. Right? 2s, I get an inner ring and then the outer ring. Here's 3s. Right? Here is my density plot of the 2s. Right? That's shown here. You might convince yourself that this value here is the most probable radius in the 2s. That's where this hangs out. And that is this ring right here. Right? That's where this thing is hanging out. When you look at these radial distribution functions, then as you go down a column, so here's a 2p, a 3p, a 4p, what you see is that these now very clearly spread out. So the 3p is definitely outside of the 4p. And it's because we have to think about these radial effects. You should be able to sketch radial distribution functions, and it's done in a similar manner as the radial wave functions. Right? So you should be able to sketch both of those things, and some of the worksheet problems will have you think about that. Here's the last worksheet problem. I'm not going to talk about that last slide, sorry. How do I calculate the most probable radius of an electron in the ground state of a hydrogen atom? I'll help you think about this. Well, remember, rho is equal to nr squared, big R squared. And if I want to find the most probable, what you're going to do is d rho dr instead of equal to 0. Right? You'll find the maxima. What's the average radius? Right? You should be able to calculate these things. And again, I'll help you here. This is r times psi star I hat psi d tau. Again, this is a triple integral. I'm just going to write it this way. I'm just going to write it as psi star. R hat is r psi r squared psi theta dr d theta d phi. Right. Group your terms, plug things in, solve, and away you go. All right, those are radial distribution functions. It's my last video for this week. We know everything there is to know about hydrogen atom wave functions. I will see you next time, and we'll talk about hydrogen atom energies.